Lecture 31 is about MOSFETs, field effect transistors. So in this lecture, we talk about the MOS capacitor under various biasing conditions, and then we talk about the operation principle of a MOSFET. So first, students should be able to identify the necessary voltage bias on the metal electrode in the MOS capacitor to induce accumulation, depletion, weak or strong inversion in the semiconductor. So this is the so-called accumulation. For a p-type semiconductor, the bulk is p-type. If we apply a voltage, a negative voltage on the metal across from the insulator, then this negative voltage will attract holes moving toward the interface. So at the interface, we're going to have a higher concentration of holes than in the bulk. That's accumulation. For n-type semiconductor, then obviously we need to apply a positive bias to attract electrons to accumulate at the interface of the semiconductor versus the oxide. So this is accumulation. And if we reverse the polarity in both cases, then we can achieve so-called depletion. So instead of attracting excess holes to the interface, now we can repel the holes away from the interface by applying a positive bias on the metal side for a p-type semiconductor, or applying a negative bias on the metal for an n-type semiconductor. This repels the charges away from the interface such that in the interface, at the surface of the semiconductor, it's less p-type than it is in the bulk, or less n-type than it is in the bulk. Now, if we further increase the magnitude of the voltage bias in the case of depletion, then we can actually push the Fermi level across the intrinsic Fermi level. So we get into the situation so-called inversion. So if you push enough holes out, then we can reduce the hole concentration so much that the whole concentration at the interface for a p-type semiconductor will actually be less than the electron concentration at the surface of the semiconductor. Or in the n-type case, we can push away so many electrons such that the electron concentration at the surface will be lower than the whole concentration at the surface. So basically, now the surface becomes n-type for a p-type semiconductor, or become p-type for n-type semiconductor. So it is inverted. Now, there's also a difference between weak inversion versus strong inversion. So for the weak inversion, we only require that the surface type is inverted from the bulk. So if the bulk is p-type, then the surface will be n-type, so electron concentration being greater than the whole concentration, both at the surface. Now, we can have a situation such that for a p-type semiconductor, the surface electron concentration could be more than the whole concentration in the bulk. Or for a n-type semiconductor, the whole concentration on the surface is more than the electron concentration in the bulk. So this is called strong inversion that obviously require a further increase in the magnitude of the voltage biases in this situation, so that the Fermi energy actually goes really close to the conduction band at the semiconductor surface. For n-type systems, for a p-type situation, the Fermi level will be really close to the conduction band edge, and for the n-type situation, n-type semiconductor situation, the Fermi energy will be really close to the valence band edge, such that the surface carrier concentrations will be inverted from what we have in the bulk and actually have higher concentrations. So these are so-called MOS capacitors, metal oxide semiconductor capacitors. You can also use them to make actual devices called MOSFETs, field effect transistor. So the second student learning outcome is that you should be able to qualitatively describe the operation principles of the MOSFET, particularly in the linear and saturation regions of the output characteristics. So these MOSFETs, obviously, when we want to turn them on, we mean that we actually create a strong inversion on the semiconductor surface. So under the gate electrode, the metal electrode we call a gate electrode, there is a strong inversion. So that requires you have a certain minimum threshold. If we have a p-type semiconductor, then we need to apply high enough gate bias to induce this electron channel. So in this case, we call it n-channel MOSFET, and this gate voltage has to be greater than a certain threshold voltage. Now, you can have a n-type semiconductor as a substrate, then you will create a p-channel, and in that case, the gate voltage will be negative if you want to generate that whole channel. So in that case, the gate voltage will be lower than a certain threshold voltage. So now let's say when the transistor is turned on, then when the drain source bias, the voltage that we apply laterally to test basically the conductance in the channel. These are so-called source and drain electrodes. So in that case, if the drain source voltage is low enough, then basically we are going to have an ohmic transport in that layer. So we have a so-called linear region. But if we apply a higher enough drain voltage, then we are going to have a higher potential in the semiconductor because of the drain voltage, and that will partially compensate for the gate bias we apply. So in this case, maybe at some point we're going to have the depletion region or the strong inversion region disappear. So we so-called pinch off. So it'll still be inverted, but it's no longer strongly inverted. It's only a weak inversion. So with this pinch off, now we're going to be seeing the current deviating significantly from the linear dependence. And actually, if the drain voltage is even higher than that, then we are going to be seeing the pinch off point moving further away from the drain source and moving closer toward the source electrode. So the increase in the drain voltage will not increase the current that we have running across the channel. Rather, it'll just be saturated. So this is the overall IV characteristics of this transistor. When we have so-called output characteristics, basically we plot the drain current as a function of the drain voltage at different gate biases. Okay, and in the linear region, we're going to have a linear dependence between the drain current and the voltage we apply between the drain source electrode. In the saturation region, it doesn't depend on the drain voltage anymore. Rather, it only depends on the gate bias or the excess gate bias we have in excess of the threshold voltage. In the linear region, obviously, the conductance does depend on the gate bias because that determines the electron, the channel, the carrier concentration in the channel, and it also depends on the mobility of the channel and also the geometry of the transistor. So in this case, the length. The channel length is the length of the channel that we have, and then the width is just in the parallel direction of these electrodes. So it is important to understand why we have a linear region and why we have a saturation region for these transistors. And obviously now if you have a slight change in the gate bias, we can induce very strong change in the current running across in the channel. That's why we call these transistors. This is the end of the review.